Checkpoints. Checkpoint 2.1. Okay, in this question, you are given a ball which is tied to a string and is moving in a horizontal circle as shown in figure 2.1a. You are asked to sketch the path of the ball if the string is released at positions X, Y, and Z. Okay, so if I were to release the string at X, according to Newton's first law, the ball at A will continue to move in direction of motion, which is in the direction of linear velocity. So the linear velocity is tangential to the circle, so I will expect the path to be this way. Okay, so it looks like this. Similarly, at Y, the tangential velocity is pointing to the left, and at Z, the tangential velocity will be pointing this direction. So when it's released at the point Z, the object will continue to move in the direction of motion, which is along this line. Okay, instead of horizontal circle, okay, now the ball is moving in a vertical circle. You're told that the string is released at the lowest position and you're asked to sketch the path. Okay, when it's released at the lowest position, same thing, we have the linear velocity, the tangential velocity, to be pointing in the horizontal direction, okay, which is to the left. But because of gravity, you find that the object cannot stay in a horizontal motion. So due to gravity, it will have to come down. So that in fact is your projectile motion. So the path described by the object will be a parabolic path. Checkpoint 2.2. A mass on the end of a string is set in motion so that it describes a circle in a horizontal plane. Okay, you're asked to identify the diagram that shows the resultant force, the direction of resultant force acting on the mass at the instant in its motion. Well, this is a past year multiple choice question. One way to do it is to draw free body diagram and then you deduce the direction of the resultant force. Or a shorter method would be, we know that the resultant force in this case is a centripetal force. Centripetal force is always directed towards the center of the circle. So we take a look at the choices. Look at this centripetal force. Okay, the circle is here. So this centripetal force is not directed towards the center of the circle. B also out, because the centripetal force can't be acting down when the object actually describes a circle in a horizontal plane. C also. D, yes. D, you can see that the centripetal force is directed towards the center of the circle. And E, no. So with that, the answer is D. Okay, so a proper way would be to look at the free body diagram, and then from there we know that the two forces acting on the object will be the tension and the weight. And to find the resultant, you complete the parallelogram. So that is the resultant force of your T and W, which have to be directed towards the center of the circle also. So answer D. Checkpoint 2.3. Here you have a pendulum bob. The mass is given as 20 grams and you are told that it's set to rotate in a horizontal circle as shown in the diagram. So this is similar to checkpoint 2.2. The time taken to complete one revolution is 1.3 seconds. So the periodic time is given. Given that the distance of the bob center of gravity from the point of suspension of the string is 50 cm. Okay, so this length here is given 50 cm. You are asked to calculate the tension T in the string. And B, you are asked to calculate the angle theta between the string and the vertical of the bob. Okay, so let's take a look at the information given. You are given the mass, given the periodic time, given the length of the string, and you're asked to find the tension T. Okay, like what I say, if you do not know how to solve this problem, start with a free body diagram. So the free body diagram for the pendulum will be that of a tension T and the weight mg. The horizontal component of tension T will give you the centripetal force. Okay, the vertical component of tension T will balance off the weight. But that one we're not interested. Okay, so let's take a look at the horizontal component. T sine theta will be equals to mr omega squared. So from here, I can find the radius in terms of the length of the string. So refer back to the diagram. Okay, so if you look at this triangle here, okay, opposite to the angle theta is the radius of the circular path. So you have the hypotenuse, which is the length of the string, 50 cm. So sine theta will be r over 50 cm. Okay, so I have r to be 0.5 sine theta. Omega is 2 pi over the periodic time. Okay, T is a tension, which is unknown. And then you also don't have sine theta. But notice that both sides sine theta, so they cancel off. From here, I get the tension in the string to be 0.23 Newton. Let's take a look at part B. Let's see what you are asked to find part B. Okay, part B you are asked to find the angle theta. Okay, so to find the angle theta, well, there are only two equations that you can form. One is resolving forces horizontally, which you have done. The other will be resolving forces vertically. So vertically, the system is in equilibrium because there is no motion in the vertical direction. It stays at that height. So the net force must be equal to 0. So I will have T cos theta to be equal to mg. Tension T already obtained from part A, which is 0.23. Mass is given as 20 gram. So convert that to kg. So the only unknown here will be theta. So from here you solve for theta, which is 31.5 degree.